Hello everyone. Today we're going to do a continuation of our lecture on voltage and current, and we're going to also talk about something called resistance. So first we're going to talk about definitions of voltage and current that we have derived last class. So first let's review our definition of electric current. Electric current is a flow of electrons or charge. Now, what it really means, it means that the electrons are all moving in the same direction. So you can see on this lovely picture that I have a bunch of electrons moving from one end of the battery into the other, and they constantly keep on moving. So it's important to notice that the flow of charge does not mean that the electrons just move. Electrons move all the time. Okay? They move around the atom. Here is a nice illustration of electrons moving around the atom. Now this is not electric current because they just move around the atom. They're not going anywhere else. So when we have an electric current, it's very much a directed movement of electrons. So it's movement of electrons in the same direction. This is very important. So the second definition we have was voltage, and we said that voltage was the force that makes electrons move. Now, it's not just the force that makes electrons move. It's the force that makes electrons move in the same direction. Because we already know that electrons move all the time, so we don't need to force them to move, right? So I want to talk more about voltage and what it really is. So I like to compare a voltage to a hedgehog from a famous Russian joke. This is a hedgehog, and the joke goes like this. A hedgehog is a proud bird. Yes, you're looking at a bird. He's not going to fly unless you kick him. So it goes exactly the same way with electrons. Electrons need something to make them move in the same direction. Okay? And that something is voltage. However, you guys remember that voltage, you can have a little bit of voltage and then the electrons move in the same direction very, very slowly. And then when you give it more voltage, the electrons move a lot faster. So it would be fair to say that electrons that move faster have more kinetic energy because they move faster. We all know that kinetic energy, if you move faster, that means you have more energy. So when we talk about voltage, it's not just the direction, it's also energy. And turns out voltage is very specific about energy. Voltage is how much energy each little electron in my electron stream has. Well, energy is something very specific. Energy has units. And units of energy are joules. They are usually abbreviated with capital J. So from these units, we can derive units for voltage. Because it's not just all the energy that everything in the current has. No, it's just the amount of energy each charge has. So So in order to do that, to specify how much energy each charge have, we need to specify the units of charge. And units of charge are not individual electrons, as you would think, because we don't always have electrons flowing. There is something called coulombs. And this one is abbreviated capital C. Now be very careful how you spell coulombs. It's pronounced coulombs, but spelled coulombs. Okay? So since we know that the voltage is how much energy each electron has in the current, right? How much energy each charge has, then the unit of voltage will be joules, how much energy, per coulomb. So this is how much energy, and coulomb is how much charge, right, each charge has. And we have a special name for that unit, and that is called a volt. And this is abbreviated with capital V. Now, all of these names are abbreviated with capital letters because they're names of the scientists. Both Joule, Coulomb, and Coulomb were French scientists, and Volta was an Italian scientist. So make sure when you're using these units to always capitalize the letter, because if you don't, the automatic grader will grade you wrong. Okay. So now that we know more about voltage, we can talk a little bit more about the relationship between current and voltage. So we know that if voltage, and voltage is usually abbreviated by the same capital letter V as its unit. If voltage goes up, we know that current will also go up. And current, and I don't know why, but it's abbreviated by capital letter I. And current also goes up, right? So we can call this relationship, we can say that voltage is current, to be honest, current. Current is directly proportional to voltage. I highly recommend knowing this. This will definitely come up on the quiz. But this is not all. We cannot just define current in terms of voltage. There has to be something else. But before we define current in terms of voltage, we need to figure out how to measure current. If we want to measure current, the best analogy I can think of to electric current is rivers, because rivers have current, only instead of electrons it's made out of water. So if I want to measure a current in a river, I would probably try and float down a stick down the river and then measure how far it went and how long it took. Well, we have a little problem with that. When you look at your current of electrons, you can't actually float a stick on top of those electrons. It's just not going to work. So we have to figure out some other kind of measurement. So if you guys recall, during the recent flood, they were releasing water from the reservoirs. And they were talking about the release rate. How many gallons per hour they're releasing. Now this is something we can definitely use to measure our electron stream. Of course, we're not going to measure gallons of water or gallons of electrons. Instead, we're going to measure how much charge in coulombs pass through a single point in 1 second. So we can stand somewhere over here. and count how many little electrons pass through this point in 1 second. So let's see, 1, 2, 3, 4. I think about 4, right? You guys can try and rewatch that segment of the video and see if that really is 4. So about about 4 charges per second. Okay. So we can measure current exactly like that. So current is measured in coulombs per second. And we have a special name for that unit. It's called ampere or amp. Most people just say amps. And the symbol for that is capital letter A. So now that we have the units for both voltage and current, it is finally time to derive an expression that relates voltage and current. But before we do that, we need to think of another quantity, and that quantity is resistance. I want you to think back to our experiment in class when we were walking around and imitating electrons. Now, it was very easy to walk because there is really nothing stopping you from doing so. Now, imagine our classroom was full of jello. Kind of like this pool, okay? And you have to walk through that. Now, imagine if you have applying exactly the same effort. Are you going to go faster or slower? Well, of course you're going to go to slower because of the friction, right? Jello is stopping you from moving fast. So the same is true for current. Current can move faster or slower depending on what it's moving through. So if you think about a wire, we already did that and said that inside the wire you have a bunch of little atoms. Let's call this iron, shall we? And then you have little electrons trying to get through, all moving in the same direction. Well, every once in a while, the electron will bump into your atom. And then it will shoot off and continue moving. So as long as it can continue moving, the current is still passing. Now, every once in a while, you have a situation where you have such a material on the other side, let's call this one silicon, that does not let the current through at all. Okay? So what is happening over here? Every single dash is represented by a pair of electrons. Now remember, electrons repel other electrons. So when this electron is trying to get through, it gets immediately repelled and literally cannot go through the structure. So if your electrons can get through the material, that material is called a conductor. And if they can't get through, it's called an insulator. And of course, there are materials that are good conductors, as in a lot of electrons can get through them without bumping into a lot of atoms. And then there are materials that are not such a good conductors and have more of those atoms that electrons bump into. To those materials, we say that they have higher resistance.